All right, today we're talking about momentum and its conservation. Conversation, yeah, that's right. It's chapter 9. In my opinion, this is one of the easiest chapters that we've done all semester. Which you may not believe me, but I don't really care about that. So, today we're going to do 9.11, impulse and momentum. There's like one big master equation that covers all this in one, and I'll show you that today. So we'll calculate momentum, we'll calculate impulse, and we'll talk about how force and time affect this impulse. So momentum is a little p, so not the capital P is power, little p is momentum. It's not m is still mass. And it kind of combines Newton's laws of inertia and F equals ma. And even the Newton's third law, where the force is comes in pairs. We'll kind of talk about that as impulse a little bit. Momentum is a vector quantity, so it has to have direction. And the definition of momentum is a little difficult. It's kind of like the measurement of inertia. It's the difference between trying to push a heavy truck versus pushing like a shopping cart. You know that it's harder to push a huge truck because it has a lot more mass. So it's going to require more force to get it to go. But it also means that it requires a lot more force to slow it down than like a shopping cart. So it's kind of a measurement of inertia, even though that's kind of a hard way to explain it. Kind of like how hard it is to get it to move or get it to change. It's moving. Has to do with mass and velocity. A little interesting. Well, I'll show you the equation first before I do it. They're on the table over there. I'm sure your clickers are. Yeah. Yeah, I have 4 clicker questions at the end of this. There's probably more germs on the outside of that Germex than there is on anything else in here. Just like those bathroom pads are probably really disgusting. What do you think about that?
These cups are probably really nasty.
I don't think the cups are that bad. I mean, your clickers are probably worse than the cups.
Wow.
Just wash your hands before you eat anything.
Just wash your hands 100%.
You need to step up. Your hands be so pretty. A few days. Wait, 2 seconds. Does he have me at 14? Oh, you do. That's exactly what I wanted you to do. You swept on your paper. You missed my 14. No, like this is my hand. You were high. Right? Yours get higher. Why are you watching?
Just trying to wait for you to be finished.
Not
so I
you.
can move on.
Not you. Oh my God.
Shorthand, bro. Shorthand.
See, when I write shorthand, I fail. So I don't think
They're on end line. I don't know how you can say it.
I don't have time for end line. Yeah. Yeah, Taylor.
All right, here's the equation for momentum. P equals mv. So anytime you have a change in momentum, either the masses they're changing or the velocity is changing. Now, for the most part, your velocity will end up being changed. So I said delta V, even though it could be delta M, that's perfectly acceptable. Most of the time it's delta V, so here's a little addition to your equations. Notice that the units for momentum are kilograms meters per second, which is kilograms is just mass, and velocity is just meters per second. So it can also be newtons times seconds, but it doesn't have its own special unit, so it's got a whole bunch of units, really.
Miss Phillips.
What?
Anything going up?
All right. The next thing I want to talk about a little bit is recoil and how important direction is. Now, we will talk about recoil, but not too terribly much yet. We'll talk about it more tomorrow. But I do want to talk about at least this part of recoil. We have a cannon, right? And let's say that it's on wheels, and the cannonball's in here. What happens if the cannon is shot forward? What happens to the cannon? It goes backwards, right? So this one, we would say, has positive velocity, and this one has negative velocity. And as we'll learn tomorrow, or I think it's next week, actually, we'll talk about conservation of momentum, where this momentum has to equal this momentum, because it started out with zero momentum. But notice that this velocity, it has a direction in it. It's a vector. So we need to make sure that we put that negative in. This also goes along with when we have collisions. We have two objects going towards each other. This one's going to have a positive velocity. This one has a negative velocity. After they hit, this one's going to go back this direction. And this one's going to go forward this direction. Right? So that velocity, that negative and the positive, is really important. You need to make sure that you include that. If you don't have that, then you're either going to end up with like double or half the velocity you're supposed to have because you've got the wrong direction on it. You can mix these up. If you prefer this one to be negative and this one to be positive, that's fine as long as you're consistent throughout the picture. Your math will end up being okay. You just need to make sure that you're consistent. And here's the big master equation. I'm going to simplify it just a little bit more for you. But impulse, it's the change in momentum. So anytime you have an outside force acting on the object, it's going to change its velocity because force is mass times acceleration. Acceleration is a change in velocity. So force changes that velocity. We call this force times time impulse. So the big master equation that I want you to write down, which looks mostly like that, it's a little bit different, is force times time equals impulse, which is the change in momentum, which is mass v final minus v initial, the change in velocity.
What's the J looking thing?
That is impulse. It's a new one. You would think, why isn't it I? But we just used moment of inertia for I in the last chapter, so we call it J. And we can even do that if you want. Now, this equation, this force times time equals the change in momentum, actually comes from F equals ma. You don't really need to write this far down, but if you're kind of interested in math or you're in calculus, it might be kind of interesting for you. Force is equal to mass times velocity, which is delta V over t. So force times time is mass times the change in velocity. So force times time is going to be the change in momentum. So it's interesting. It's not really something you need to know, but it's kind of neat. So this one up here at the very top, that's the equation you want to write down. And we only use pieces from it that you need. You don't have to use the whole thing. Because a lot of times you're not given all of those things. You're only given pieces. So just use the pieces that you need. And I'll show you what I mean. This is a force times time graph. When you graph force times time, you get the impulse of it. And you can see that the force as it acts, it's not just like 5 newtons. It gradually increases up to the maximum and then goes back down. So it's not a nice, easy 5 newtons. You can imagine this by, here's a duck. The duck hits an object, it hits the surface. Let's say like a table or the ground or the wall. As it goes, as it hits, it's flying and it hits, and it's very light at first, and then it still has momentum, so it keeps going in, going in, going in, going in until it's maximum force. And then it starts to rebound, it starts to go back, and it gets less and less and less and less until it leaves. Because objects, they're not, instantaneous. They deform a little bit, and even if they didn't deform a little bit, they have to touch just a little bit as they turn around. You get to that maximum force. So when we're talking about this force times time, we're actually talking about the average force. So the average force is like, cut this thing in half, like here-ish, that's going to be your average force. For people that are in calculus, the integral of force times force with respect to time is your impulse. So if you calculate the area under this curve, you'll get the impulse. But usually, for this class, we'll just talk about it as average force, even though it is not one single force over that amount of time. All right, so let's do a practice. We have a 2,200 kilogram car. It's going 94 kilometers an hour, and it hits a wall. It is. That's not bad. It's not good. Okay, so it makes contact with the wall for 0.2 seconds, and then it stops. So we've got a nice picture up there. We'll leave that picture. That's fine. Let's look at our numbers. We have 2,200 kilograms. We have 94 kilometers an hour, 0.2 seconds. What's this 2,200 kilograms? Yes. What about the 94 kilometers an hour? Good. Velocity. And the 0.2 seconds? Time. What is hidden in there? That doesn't really give us a number, but it is a number. It stops. So that means that it's not going anywhere. And which variable is that? V. And you're right, it is V final, so that makes this V initial. Okay, part A. What's part A asking for? This is momentum initial, right? So what variable is that? P initial, right? Pi. Okay, so let's calculate that. I'm going to calculate that off to the side here. We have Part A, PI. What's the equation for momentum? Mass times velocity, and this is initial velocity. So we should have PI equals 2,200 times, what's wrong with our VI? Anybody see what's wrong with it? It's in kilometers an hour, so we need to change this so it's not in kilometers an hour. What am I going to multiply it by here? What's the first one? 1,000 meters over 1 kilometer. And how about the second one? 1 hour over 3,600 seconds. You should memorize that one. We use that one a lot. So it's like 94 divided by 3.6 in the end. So we get 26.1. That's our new initial velocity. So let's put that 26.1 in here. And what do we get? I messed that one up. 5.7. I got 4.20. Is that right? Good. Questions about that one? All right, and then B. What's B asking for? Final what? Momentum. So momentum final. M times VF. Mass is 2,200. What's VF? 0. So the whole thing is 0. All right. Part C. What's the impulse? What variable are we looking for? J. Good. Now, that's where this equation comes in. Let's look at this. We are looking for J. What are we given? We're given mass and velocity in the problem, so we could use that, but we just calculated PI and PF, so this part of the equation is a little bit better. So we're going to use J equals delta P, which is P final minus P initial. So J is going to be P final, which was 0, minus P initial, which is 57420. So J is just negative 57420. And this, you can either put newtons seconds or kilograms meters per second. Doesn't matter. Why is it negative? That's why. It's because it's stopping. The force of the wall is applying it in the opposite direction in which the car initially was moving. So that's why it's negative. Impulse is in the opposite direction. Okay, part D. With what force does it hit the wall with? What variable are we looking for? F. All right. So what parts of the equation do we want to use? I mean, the part with F in it, right? And what else? Which one of these? It doesn't really matter. We have all the pieces. But this one's probably the easiest. So force times time equals J. Force is what we're looking for. Time was 0.2. And J is this negative 57420. There we go. So force is going to be 57420 divided by 0.2. That gives you 2.87 times 10 to the 5 newtons, and it's acting in the opposite direction the car was initially going. Which makes it negative. Okay. Any questions about this? This is a basic run through. Okay, I have 4 clicker questions for you today. I'll probably make it through all of them. So you guys are so quiet. So here's the first one. A 1,500 kilogram car hits a wall with a velocity of 20 meters per second and it immediately comes to rest. What is the final momentum? Notice it says, what's the final momentum?